Okay, so last time we left off on Bent's rule, and this is actually the rationalizing the experimental bond angles in Bent's rule. And so when we have, why are we seeing this pattern right here real quick? So SF2, smaller angle, SCL2, larger angle, and so on.
It's a decrease in electronegativity of the ligands. So
Exactly.
ligands would be larger.
Exactly. Yeah. You got it. Perfect. Yep. It's the electronegativity difference between the sulfur and the fluorine, right? And we can actually predict these using the Bent's rule formula. If you remember your Bent's rule formula that we did just a bit ago. Okay. All right. So again, all of the molecules are going to have that tetrahedral electron geometry, right? And so you need to use the Bent molecular geometries. You would then take that percent S character calculation, you'd plug that in, and you would actually get numbers that are very, very close to these. And you see again, that is the percent S character right there, right? So as we see, this is just directly the pattern of your percent S character, okay? So for example, this one right here, which is the SF2, these are very high in P character, right? And so they're more narrow, pushed out towards the fluorine, right? And over here we have a lesser S character. They're less narrow, more towards the sulfur than the fluorines, right? For electron density, okay? And then you have more S character right here for the bromine, because again, that's less electronegativity difference. Okay. All right. So different types of ligands on the central atom, like CH3Cl is going to cause hybridization parameters. And so you would actually get a hybridization of your parameters due to these. And you'll get a cosine ij. So when you're looking at these, you're actually going to end up with, again, ligands I and J, which would be your two different types of ligands, in this case, hydrogen and chlorine, right? And you would use these set of formulas right here to calculate this. So again, this is the S decimal percent S character for that SPN hybridization, whatever the hybridization happens to be. In this case, it would be SP3, right? Because we have 4 groups. Okay. And then the P is going to be the decimal character right here. That is the P character. And you notice that's actually a reversion of that. Everybody see that okay? Okay. And so theta is going to be the naturally occurring angle between them. It's theta right there. So that's going to be the angle between these two different IJ. So a hydrogen chlorine angle, right? Hydrogen carbon chlorine angle. Okay. And then you'd put in this value for the I and the J. Okay. And that will give you, well, vice versa. If you know the angle, this would give you these values right here, right? Okay. And then you can sub one into the other. All right. So let's look at hypervalent molecules. Another name for this is hypercoordination. And so if we look at this right here, which is the PF5, you guys have probably seen that a few times. This actually does not work well as what we've previously been talking about, okay? And that's that it doesn't really have each of these are bonds, normal bonds, okay. What it actually has is the phosphorus here is actually ionic because it's had so much electron density pulled away from it. It's actually positive, okay? And then one of the fluorines is actually going to be in the form of fluoride. And this is going to coordinate to that phosphorus. Okay. All right. And notice these are just the different geometries here. Okay. This would be your resonance structures here. And so what you end up getting is you get the 5 ionic canonical structures in your resonant hybrid for PF5. And so these bonds end up being partially normal sigma bonds and partially ionic. Or another way of saying is they have a lot of ionic character. Okay? Or a lot of coordination character. Okay. All right. So this is a 3-centered 4-electron bonding. This is actually what it looks like along the z-axis. And you can see that here we actually see a non-bonding orbital being filled in. Okay? And so what that is energetically that would be equivalent to it just being on the individual atoms. It doesn't take away from the bonding being more stable, but it doesn't add to it either. Okay? This would still bond because these bonding orbitals are lower energy, and so that would still prompt bonding. Okay? Does anybody know what would happen if we filled in 2 electrons up here in the anti-bonding orbital? So there is nodes. This is anywhere these would combine where it's the black with the white would be nodes. Yeah. And that's why these are the anti-bonding ones. But again, if we were to add 2 electrons to this, these would cancel any energy gains here out, right? And so that would become less stable, and that would mean you'd have no stability gains, no energy gains from bonding. Okay? And that would tell you that this would not bond. It would have a 0 bond order, it doesn't bond. Okay? Okay, so let's start talking about sigma and pi bonding. So the sigma and pi bonding, you guys may have always kind of wondered how the hell did they get sigma and pi for these bonds. And that's actually from, remember our symmetry? There was the capital sigmas when we were talking about our irreducible representations. So if you looked at the character tables, you would have noticed D infinite H there has a sigma G plus on that left side column, right? Everybody okay with that? Okay. Okay, and that's actually where the sigma bonding nomenclature comes from. It actually comes from that sigma, and that's because that bonding axis is actually, for that point group, is actually what's used as a basis set for that bonding, the sigma bonding. Okay? And so that's actually the sigma. It's just a lowercase sigma in this case for the bond versus the capital sigma here. Okay. The pi is actually very similar. So your pi, you have 2 atomic orbitals that are going to overlap in a sideways fashion, of course, sigma being a direct overlap, right? Okay. And so there is going to be a nodal plane. This is going to be along that internuclear axis. So it's above and below, right? And you have a nodal plane in between. Okay. This is why these are always a little higher energy, a little lower energy, right? Because you already have that nodal plane. So it's always why their lowest energy one's always higher energy because you already have the node in any pi bonding. Your pi bond is, again, going to be the basis set representing the sideways orbital overlap transformations. This right here being capital pi U plus. This is its irreducible representation, would represent that symmetry. And your D infinity H point group again. And so the language for those came from the D infinity H point group, which the pi bond is represented here on the pi U plus, and the sigma bond would be represented within the sigma G plus in IRR, irreducible representation. Okay, so let's go ahead and look at some sigma bonds and where the coaxial overlap of combining these atomic orbitals. So this right here is one sigma bond, and that's probably the most familiar you would have is just direct s orbitals overlapping, and you get a nice orbital overlap, right? However, you may actually see things like the SPZ. So this right here would be an s orbital, which is just sphere, right? And then this over here would be your p orbitals. And so you have the plus and plus constructively overlapping, the dark, and that gives you that direct overlap, which is a sigma bond again. Everybody okay with that so far? Okay, am I losing anybody yet? Fantastic. Okay, this would be a p orbital overlap. By a convention, you would use the pz because that's the top, right? And so you just use PZ to do these. And that's, again, a direct orbital overlap. And over here, we actually see the PZ overlapping with a d orbital, right? And then again, this would be your most commonly used by convention. First one that you would use would be the dx2 minus the y2. Did anybody remember the d orbitals? The 5 d orbitals? Yeah, and that's one of those 5 d orbitals, right?
Just one of the orbitals?
Yeah. Yeah. So if you remember your d orbitals, most of them look like clovers, right?
Right, and will they take the space up that the other orbitals are not occupying, right?
Yeah, yeah. And so this right here is in the x and y plane. This is that clover-looking one in the xy plane. And then you have the z equivalent. You have the... Does that make sense? Okay. This right here is going to be where you do pi bonding. And you notice that you can't get a pi bond with s orbitals. Why can't you get pi bonds with s orbitals? Can you get an indirect overlap with a sphere? A single sphere? That surrounds the thing in the middle? You can't get an indirect overlap, can you? Okay? So, if you ever get an s orbital involved in a pi bond, something's wrong. You want to double check that. Okay. So this is going to be your px's, because again, you typically center your z's pointing towards each other to make life a little easier. And then your x's would be the ones pointing upwards in this case. Okay. And so this is going to be the indirect overlap of your p orbitals, and that gives you your pi bond, right? All right. Very good. And so these are the atomic orbitals, px on the two different atoms, and that gives you a pi orbital overlap, right? Okay. Notice this is only one of the molecular orbitals. How many molecular orbitals is actually made? If two orbitals come in, how many has to come out? 2. Same number, right? So whenever you look at these, and we're describing the bonding orbitals, aren't we? And we only ever describe the bonding orbitals, okay? We always skip the anti-bonding orbitals when we're talking about these on the basis, okay? When we're introducing these concepts, okay? The anti-bonding orbitals would actually just be one of these flipped. And that would give you your node right here. Okay? So this would be white up here, this would be black. They destructively interfere with each other where they overlap, and you'd find no electrons there. Is that making some sense? Okay. Okay. Very common issue people have with this is, like, why are we only getting one orbital? And it's because we're only looking at the bonding, right? Bonding orbitals. We're not looking at anti-bonding orbitals. Okay. Okay, and so this is going to be the other pi bonding orbital, and this is going to be the px overlapping with the dxz. And so you see again here you get matching constructive interference. Okay, and again you get overlap on the side, don't you? Okay. Okay. All right, so this is going to be your hybridization with an sp2 hybridization, and you can see that this is what molecule? If you have an sp2 hybridization, what does that tell you about this? Double bond, yeah. So if you go back to your organic chemistry, sp2 hybridization on that carbon tells you it has a double bond, doesn't it? Okay. And that's actually what you're seeing right here. This is the overlapping 2pz and 2pz on these two carbons here, right? Okay. All right. And so this is your spxpy hybridization. Again, this is going to force this molecule into the xy plane here, right? Because your double bond, your pi bond, is going to be above and below. And everybody sees that in the one plane, right? Okay. Again, this would be how you'd write out orbitals in the proper way. And so you take your orbitals here, You do a promotion. This is going to be representing your hybridization. Can everybody see that okay? Where we unpaired all of these, so we get our SPs, right? So we do the promotion here. This is that first step into getting your hybridization. Okay? So this is freeing up your orbitals so you can actually get them distributed. Okay? So we're going to hybridize. In this case, because we're only matching up with these 4 hydrogens right here, we only need how many unpaired hybridized orbitals? So we have 2 carbons, right? And 4 hydrogens. Okay? And so because of that geometry, the sp2 hybridized orbitals are the ones we need to make here, aren't they? And we need 1 free p orbital. Okay? Because the sp3 hybridized orbitals would not be able to make an above and below overlap, would they? Because they have directionality to them. All right? Is everybody understanding that one? Okay. Okay. And so we hybridize now. This is going to give us no energy cost. That promotion does cost us energy, by the way. Notice, by the way, you actually usually flip by designation, have your other set of molecules have the opposite spin, because what you're doing is you're setting up a situation where you're going to pair these electrons into molecular orbitals, aren't you? Okay. And so you want 1 up, 1 down, so they pair. Okay. The next step you're going to do here is once you've hybridized, you're going to go ahead and do your bond formations after that. This is actually going to help you dictate your geometry. And so right here we have our sp2 hybridized orbitals. Those are 3 single bonds that are going to be made around here, right? This is going to have the same thing but reflected. So those are our sp2 hybridized orbitals right here. Okay? And that's going to involve making your single bonds. So we go ahead and put these together, and these are going to give us our molecular orbitals right here, making our bonds. They'll be composed of an s hydrogen orbital and an sp2 hybridized carbon orbital, okay, with 2 electrons in that. Okay, that's then our bonding right there. This is the pi overlap. That's actually constructed from the 2 pz orbitals on the 2 carbons. Okay, and that's that pi bond. Okay, did everybody keep along with me? Fantastic. Fantastic. Okay. All right, so this right here is actually the Fe3 plus, and you've maybe seen a few of these now, where it's Fe with some sort of ligands attached to it. Usually it has a positive charge still. And so this actually is the one that gives you the hybridization, so you can figure out the hybridization for this, because this gives you your Vesper model, right? Maximum separation for 6 things. Okay. Okay. Why are these arrows like that? Weird arrows, right?
They're attracted to the charge.
Yeah, so ligands are typically going to have lone pairs. Okay? And so they're going to be something that has electron density. It can then donate into a bond. And so these are going to be coordinate bonds. You may have noticed we had started talking about coordination, right? Okay. And so this is going to be coordination where these donate an electron pair to that Fe3+. The Fe3+, even though it's iron, it has a 3+ charge, right? And so it's a much better, it's much more electronegative than iron would typically be, right? Because it has the 3+ charge. So it can attract those electrons much better than normal. Okay? And so what's going to happen is those electrons are going to be grabbed by the iron, and they're going to form something that's very similar to a covalent bond. Okay? It's mostly covalent bond character. And that's going to give you a coordinate bond. The coordinate part, coordinate covalent bond, if it's a fully covalent bond. And you may recognize that from back in acid bases and organic chemistry. Okay, It's the type of bond typically made when you take like a base and then react it with an H plus, and it gives the electrons into a covalent bond, right? Okay. So, again, this is a coordination. The electrons are going to be given by the ligand into a bond with the Fe3 plus. Okay, let's go ahead and look at the orbital diagram. And here we have our orbital diagram again. And so normally this is what you would see for Fe3 plus in terms of your orbitals. Everything would be split out. Now recognize that Fe3 plus has a 3 plus charge. It has a lot less shielding that would go on, right? Or another way of saying that is it has a lot more pull from the nucleus. And do you remember our previous work that we talked about? If you have more pull from that nucleus because you have more positive charge, which orbital is lower in energy from that the most? That's the d orbitals that lower in energy the most from that, isn't it? Okay. And so what you're saying is these actually get flipped. You actually end up lowering that energy for the d orbitals. And so you end up distributing 1 electron for each d orbital. And that's going to be your lowest energy. Now, for your hybridization, though, you need to pair these up to get the correct hybridization later, because these are going to require empty orbitals, and that's because your ligands have no places to put electrons, do they? Okay, they have full orbitals. Everybody see that okay? And so the orbitals that are being donated by the iron have to be what? Empty. Yeah, have to be open, right? You can't have electrons in the orbitals donated by the iron, can you? Because there'd be nowhere to put the ligand or electrons. Okay? And so this is kind of an interesting thing, where this actually kind of is almost the exact opposite of what you were doing before, right? Before, you were distributing out those electrons, even if they're higher energy orbitals, so that you could pair them up, right? And that's because that was a typical covalent bond, where each of them donates an electron. Okay. By the way, I do need to try to get through this material fairly quickly. I really need to finish this up today. So if I hit a block, I might end up going like, ask me questions, okay? Because we really want to get to chapter 10 and 11. That's like a lot of inorganic chemistry that you guys might encounter, okay? This stuff's kind of like interesting, but ish. There's not a lot of orbital stuff you need to do. It's just not a career. Anyways, is everybody okay with this, that you need the unpaired orbitals to make your bonds here? And so that's why we're hybridizing these. That's also why we need the hybridization here that we're getting, where we take the S, then the P's, then we need 2 more d orbitals, right? Because that only gives you 4, we need 6. Everybody okay with that part? Okay. Did I lose anybody? Okay, fantastic. All right, so this right here is a molecular orbital diagram for H2 plus. You'll see that H2 plus is oftentimes used because it's the simplest molecule you can make. Okay, so if you're gonna do calculations for actual wave mechanics of these electrons, then H2 plus is what you kind of have to do, okay? Because it's one of the few ones you can actually solve, because it only has 3 bodies, 3 things that are attracting each other, okay? It's something you can get very close to solving. I believe this one actually has been solved by a quantum computer. If I remember correctly, they have not gotten H2 with no charge yet, but I'd have to see. They may have snuck it in last year. Okay, so this is again going to be 2 orbitals. They're s orbitals from each of your hydrogens. They're going to mix to give you your bonding and anti-bonding orbital, and we'll have 1 electron. And the cool thing about this is you can actually see the wave function for this having combined together. So each of these orbitals would have had a wave function, an equation that would describe those electrons moving in those orbitals. If you actually combine them together, this is what you get. Okay? And so this is your direct overlap. This is your sigma bond using 2 s orbitals. Okay? This right here is your anti-bonding destructive overlap. Do you see your node? Right there. Yeah. So typically in these orbitals, what you'll see is that the most common reason for these orbitals to go up in energy is actually addition of nodes. And in most of these, where you're not doing full calculations, you would consider the ones that don't have differences in node numbers as sort of being like equivalent in energy. And you wouldn't really differentiate them. Okay? And that's the typical organic approach. So this right here is actually those wave functions for those electrons if you had no bonding at all. Okay? And so you see there's no interference in that tail off. You have the highest probability of finding an electron directly around the nucleus, right? And then it tails off as you go further. What you'll see here is as you bond, what's going to happen to that probability. What's going to happen? Is it going to tail off and as you go to the center? No. It's going to increase as you go to the right around the nucleus, right? Okay. And you'll get a lowest spot that you can find it that's going to be directly between them. Okay.
So this is talking about the energy.
This is talking about probability of finding the electrons.
Oh.
Yeah. So these are your nuclei right here. This would be your bond distance here. And this right here would be the bond. And so actually you have a lower probability of finding the electrons directly between the two nuclei than you do around the nuclei. And that's kind of a funny thing because you can't really see that when you look at normal orbitals because there's 90% chance of seeing it, right? So it just looks like you just find the highest probability between, doesn't it? Yeah. But that's not true. And then as you get further out from the nucleus, you're going to see that probability trails off quite a bit. Okay? And that's why you trails off as you go like this. That is this. Okay? Okay. All right. This right here is actually the destructive interference. Can everybody see that okay? So what we have here is opposite orbitals. That would be that black and white, right? And so they're destructively interfering with each other. And so your probability between them actually goes to 0. And you actually have higher probability of finding them on opposite sides of the nucleus. Okay? Everybody okay with that? And guess what this is, where you have a probability of 0? No. Yeah, that's your node. By the way, this is just the row here, and this one here is the squared. So they're positive. That's why it's more drastically curved. This tells you just basic probabilities. This one also has the fact that it's a positive negative. Yeah. Okay, and so conservation of orbitals must apply whenever you do this molecular orbital generations. The number of atomic orbitals has to equal the number of molecular orbitals. The energies of the combining atomic orbitals must be similar to the weighing coefficients to be significant. The combining orbitals must have a non-zero overlap, so you have to have some degree of overlap to have a combination. So if you have two orbitals that have no overlap, px, pz, you can't get any bonding, right? Okay. The symmetries of the combining, just to be clear, I was talking about pi bond there. If you had two orbitals like this, right? If you had it like this, you could overlap. Okay. The symmetries of the combining orbitals must be the same. This is actually where group theory comes in. We're not going to go a lot on this because it's just not relevant for almost any of you to go in your careers. But if you ever needed to go back, because you actually do get into this somehow in grad school, which there is a contingent of people that do, you know the book, okay? And you can always talk to me, talk to people. You know where to get it. I just can't give you every single piece of information because this class would be very long. All right. So the one electron molecular orbital diagram, this is actually for H2. Again, this is that calculation, and you can see in this case, we don't just have one electron in this, we have two, but really doesn't do anything to this, does it? Looks extremely similar to the other one, right? Because again, they're going to end up in similar places because you can have the two spins of electrons, right? And so you'd find them in the same orbital set, okay? If we had an extra electron, that would start popping up into here. And that electron would have to go into here, one of this area. Okay? Okay. All right, so this is actually how you figure out bond order, excuse me. And so, shit. Okay, so this is how you'd figure out bond order. So in this case, what you're seeing here is this is our bonding and anti-bonding orbitals, right? And so what you always do is you take 1/2 of your bonding minus your anti-bonding orbitals. Okay? So your bond order for this one right here is what? So that would be 2 minus 0, divide by 2, and that gives you 1 bond, right? Okay. This one here, 2 minus 2, 0, and so we don't bond, do we? Okay. So there's not actually bonding for this. This would be heliums, and this is why helium is not a diatomic gas. It's actually just not energetically favorable to make bonds. Now, interestingly enough, helium does associate with each other more than some gases. And this actually is why you can find some helium-2s like every now and then, because it's not super energetically inefficient. So you can get some population.
Is the anti-bonding always going to be on the top?
Yes. Yeah. Because they'll always be higher energy.
Oh.
Yeah. So you always make your bonding lower energy, anti-bonding higher energy. And that's actually by definition. So your atomic orbitals here, if you average those, you would get a line. And then anything below that line is always bonding. And that's why it's bonding, is it's energetically favorable from being individual. Anything on top then is always anti-bonding because it's energetically unfavorable. If you go into that, you're actually going to want to come back apart, right? Because it's lower energy to be apart. And anything on the line is actually going to be non-bonding. It just neither direction. Okay. By the way, same terminology was for the aromatic, aromatic, anti-aromatic, non-aromatic, and that's because it is this stuff. Okay, and this is your nodes here again. So remember, we're looking at here. So we have direct overlap. In this case, this is p orbitals directly overlapping, still a sigma bond, right? And then we have a node here, and that's our anti-sigma, or our anti-bonding sigma. Okay? What does the star mean, by the way? It means excited state, high energy state. Okay? It's actually just designated for high energy. In these cases, they're always anti-bonding orbitals because they're higher energy. But yeah, so this right here is going to be your pi bonds, and so pi bonds are never the lowest energy bonds. Why? What do you see there? We have a built-in node, dang it. Okay, it's not quite as effective of a node as the other one. It's not as high energy of a node because we still have sharing here, right? But we have a node in our lowest energy one, don't we? Damn. And then our next one, our anti-bonding one, would have another node, wouldn't it? Okay. By the way, if you got pi bonding conjugated systems, you would also have sets of where they have no nodes and they all line up, like the conjugated systems you are probably thinking of, where the electrons can freely go around it. But you'd also have ones that are higher energy that would have nodes, an extra node. So half of them are up, half of them are down. You got one extra node from where they join. Okay, and so this right here is just that same sort of one electron molecular diagram, but this one's for O2. And again, we generate it the same way. It's just to give you a sort of idea what these look like. And you can see pretty clearly, like this right here is your direct overlap sigmas, right, where you have the s orbitals. This right here would be the p orbital direct overlaps. So those would be your sigmas, p orbitals. And these here would be your pi bonding, right? Okay. And if you had a triple bond, you'd have one above and below, one on the other direction, right? And that would actually be due to the px matching, py matching, right? Okay. And pz's are typically by definition pointed in. Okay. Okay, and so we're going to actually see one more kind of unique case here. So whenever we have molecular orbitals that have the same symmetry and similar energies, they're actually going to mix with each other. In extreme cases, this can actually lead to a molecular orbital diagrams that we see over here because they actually mix and change energies because of the mixing. Okay, okay. So what we're seeing here is we have two molecular orbital diagrams for the two parts. This is the S and P's, right? Mixing together. And then what we see here is we actually end up with something that's kind of like hybridization, isn't it? So we have the sigma S's and the sigma P's, and they end up mixing together. Okay? And it is very similar to hybridization. You can think of it as just hybridization in molecules. Okay? And so these energies are similar enough that we actually get mixing of them. And what we see is this one actually goes down in energy. So the anti-bonding actually gets pushed down. And this bonding right here actually jumps all the way up to above the pi bond. Okay? And this actually becomes very important for certain molecules where you would have like paramagnetism versus diamagnetism on paired electrons and orbitals versus non-on-paired, right? Because this could cause different pairing, couldn't it? Like, what if we had had this one filled with 2 electrons and nothing in these? Well, if this mixing occurs, then we're going to have 2 unpaired electrons in the pi, right? Yeah. Okay. And again, this has to do with how the electrons are structured in this. Sometimes you get mixing of those orbitals, right? And so it depresses one and increases the other to move those out. You get kind of a reinforcement of one position and then a moving out of the others to higher energy. Okay, so this is a mixing molecular orbital diagram. This is for a period 2 homonuclear, same on both sides, diatomic. We're actually going to generate this with sp hybrid orbitals on each atom. And we're going to do that before combining the valence orbitals to form molecular orbitals. And so mixing typically occurs on B2, C2, and N2. So those are some of the most important ones that would cause mixing. And that's where you'd see this molecular orbital diagram right here, okay? So that's B2, C2, and N2. Man, I need like a big bottle of water that I keep here for Tuesdays only. Okay. I'm dying. All right, so notice here that what we've done is we've hybridized these to an sp hybridization. Can everybody see that okay? Okay. And we've combined these s and p orbitals, giving us our sp hybrid orbitals right here. We've combined an s and p orbital, and that gives us our sp orbitals right here, right? And if we do that before, what we'll end up seeing is that we actually see that change in energy from their hybridized orbitals, right? So this mixing was just hybridization being applied after you make your molecular orbitals, okay? All right. And so you can see that we actually end up with this next sigma actually ends up boosted, and that's because it actually has a lot of p character in it, doesn't it? Okay. Whereas this sigma actually gets lowered. right here. So we actually end up with a lowering down here. Okay. Anybody have any questions about that so far? Okay. All right. So this is going to be your no mixing versus mixing here. And you can see again what we get is a lowering and then a boosting. And so that same relationship that we'd been looking at before, where your molecular orbitals always end up being approximately the average of your atomic orbitals, still holds true, right? It's just that, again, it's the mixing causes a boosting versus a non-boosting. Okay, so what we're seeing here is these are, again, the direct overlap. Then we have the deconstructive interference right here, right? Okay. So what we would notice here is if we go ahead and look at the mixing one, which would be the hybridization, what do you notice about this constructive interference? The positive interaction is maximized, isn't it? And these big orbitals pointing towards each other now, don't we? Okay. What do we notice about the destructive interference here? We've minimized that, haven't we? So we've minimized the other one a little bit right here. See that? We minimized these. Okay. And so this one's the higher energy because we've minimized that overlap here, haven't we? This one's lower energy because we maximized the overlap here. Okay. This one's the lower energy because we've minimized the destructive interferences. This one's higher energy because we've maximized them, okay, due to our hybridization. All right, and so this is just that mixing procedure where we've looked at it in terms of hybridization. Okay. All right, so let's look a bit at the percent ionic character. Good grief. Can you guys see any of that? Kind of. All right. Okay. So this one here is hydrogen, and that's covalent, right? And so what we see is a 50-50 split between the electron density between them. And what do you notice about the orbitals here, the bonding versus anti-bonding? Which do they look like? The bonding is filled, but the bonding, for example, really doesn't look like either, does it? It looks like both combined, doesn't it? Okay? And that's because both of them are contributing 50-50. Okay? If we look at something that's more ionic, so we have a 28% lithium. Lithium's right here. We have a 72% hydrogen right here. What we notice is the lower energy orbital is going to look like and be closest to the hydrogen, because that's the one that is holding on to more electron density, isn't it? It's the more electronegative one. Okay. Over here we see that the higher energy orbital, the anti-bonding one, is the lithium, isn't it? Because that one holds on to a lot less electron density. That is a lower negativity. So it's going to have the electrons pulled from it. Okay. And that's the higher energy state. That's basically what you would have expected if you thought about it, right? Is that the higher electronegativity thing is going to be lower energy for the electrons to be there. The lower electronegativity thing is going to be higher energy for the electrons to be over there, isn't it? Okay? Yeah. It actually makes a lot of sense once you start thinking about it. So this right here is actually a molecular diagram for a linear H3 minus molecular ion. And you can actually see here the different overlaps in terms of the bonding here. And so, for example, this one right here is your bonding sigma. That's that direct overlap, and that's where all three of those s orbitals are overlapping constructively. Okay. When you get the middle one here as not contributing, and then you get the two opposite ones on the two sides, that's when you're going to see that next highest energy. And this one here is essentially a non-bonding, right? Can everybody see that? That's equivalent in energy to this just not bonding. Because in reality, it kind of isn't. You have one of the atoms that's just not taking part, right? Mm-hmm.
Why does that then have electrons in it?
What do you mean?
Like, why wouldn't it prefer to be in the unpaired one that's low energy?
it prefers, because this one's full, and so you have to put the electrons in another state. And the next state up would be anti-bonding, a very high energy state, where you have two nodes.
You couldn't, like I'm saying, a single one on the.
Yeah. So this one right here is actually being held in this state by the fact that these are more energetically favorable.
Okay.
So when you look at the overall energetics, right? That's why like any reaction that's non-spontaneous happens, is because you push energy into it, right?
Okay.
You couple it with something else. And so what we have here is this one here is not energetically favorable to anything or unfavorable. It's equivalent. If this was the only thing, then this was just basically form and on-form all the time. And no overall. But it's coupled to that one. And that one's energetically favorable. Not a lot. Not a lot, right? But a little. Okay. And yeah, this is not particularly stable, as you can tell from the energy diagram, right? Yeah. This is not particularly unstable. This is hydrogen with a negative charge. It's more stable than having hydride. Hydride is one of the most reactive substances you could buy, right? So it's not as stable, but it's stabler than having a hydride in H2. So the electron contour diagram, this is that linear H3 minus molecule, and what you actually see is you kind of see the nodes a little bit, don't you? Can you see that vacated spots that sort of tail out towards the middle? And that's because that middle actually is where you kind of get a node on this previous one. And you can actually see the nodes here. You guys see that? That reduces that electron density a bit. Yeah, so this gets sucked in right there because you actually experience less electron density around the middle because it's the pass-through point. Okay, this right here is actually a comparison of your lowest energy solutions to your particle in the box model. Particle in the box is how you'd model these wave functions in a confined space so that you can kind of see where they would likely occur. And what you see right here is this one right here actually shares the electrons in between, and that's actually the one that contributes the most electron density to the middle area. Okay. This one right here has a node right there, right? So you don't get any electron density. And then this one has nodes on both sides, right there and there. Okay. Anybody have any questions about that material? I actually finished up before I thought I would. So I thought I was going to take forever for the last ones, honestly. But no, you guys seem to grasp it pretty well. So, does anybody have any questions at all? If not, I guess we'll just call it a day, and we'll go on to Chapter 8 next time. Did everybody see that there's homework? Okay. And I've purposely avoided some questions on this. I'm avoiding the going too far into group theory because I really want to get you guys to ligands and organometallic chemistry. And if I deep dive into the group theory and doing the reducible representations, I'm pretty sure that's going to be another 2 weeks. And I don't think we have time for that. Okay? If you ever want to, let me know. I would love to find out that I should deep dive into group theory. That'd be awesome. So when you guys go to grad school and go out into your jobs, if you actually was like, man, I really regret that you didn't make us deep dive into the linear algebra and group theory, please call me and complain to me. Okay? Seriously, I'm serious. But I'm pretty sure organic metallic chemistry is going to be much more useful for all of you. Just blow it out of the water difference. Yeah. Anybody have any questions at all? Any comments? Tap dance routines? Party tricks? No?
So the next test would be for first, and that'll just be 7, 8, and 9?
So it's actually going to be 10 as well. And I actually will have moved the test back, I believe, on the dynamic sheet. So if you ever want the most up-to-date picture of what's going on with me, this is actually my scheduling sheet, and that's that one that's on the syllabus page. Okay. And I only recently realized, because I didn't get the damn book until several weeks after the course started, that the titles for these last couple chapters, 9 and 10, could have meant two things. And I didn't realize that one of the things I need to test you guys on chapter exam 2 to justify the course when accreditation comes around is in chapter 10, actually, not in chapter 9. So I had to move chapter 10 into exam 2 and move exam 2 back. Okay. And then we'll do 11, 12, and 13. 11 actually is the organic metallic starting, and then this is just more stuff. But as long as I get you through 11 and part of the way through 12, I'll feel happy. And we did it. Got you all the key things.